My name is Nikita. I am from BSc Chemistry Honors second year. Now I am tell us about the second law of thermodynamics. Need for the second law of thermodynamics. First law of thermodynamics is merely the law of conversion of energy. There are several phenomena which cannot be explained by the first law. The first law is not sufficient as certain limitations which are discussed as follow. First law does not restriction on the direction of flow of heat. First law establishes the relation between the heat absorbed and work is done by the system. It placed no restriction on the source of heat or on the direction of its flow. According to first law of thermodynamics, it is possible to heat water using ice without any external efforts, yet we know from experience that such a transfer of heat from lower temperature to high temperature will not take place spontaneously. Heat is always found to flow from hotter to colder body. Thus, first law is unable to tell the direction of flow heat. It is only indicate that if such process occur, then the heat gain will be exactly equal the heat loss. Similarly, the first law cannot predicate whether a gas can diffuse from low pressure to high pressure or water can flow uphill on its own or not. Thus first law provide no information regarding the feasibility of the process. The second law of thermodynamics help us to determine the direction in which energy can transfer. First law has no certainty for spontaneous of a process. There are several natural processes which take place of their own its own direction, but they do not proceed in a reverse direction or their own. For example, water flow the hill but cannot flow up the hill its own. Flow of it from warm to colder body, expansion of gas into a vacuum, burning of fuel, etc. are some example of process which take place only in one particular direction. Such processes are called spontaneous process. According to first light was suggested the decrease of heat content in the region for spontaneous. This means that a reaction in which heat is involved must be spontaneous, whereas a reaction in which heat is absorbed must be non-spontaneous. But there are some processes in which delta U is positive, still the reaction proceeds spontaneously, such as vaporization of a water at lower pressure. H2O liquid react with in the presence of 298 Kelvin and 1.0 Kelvin pressure H2O gas. Hence, delta U cannot be certainty for spontaneous. Similarly, delta H cannot be used for predicating spontaneous because there are many reactions which are processed spontaneously with a positive value of delta H. Example, dilution of NH4Cl solid in water. Thus, it is seen that function U and H derived from the first law of thermodynamics cannot predicate the spontaneous of reaction, and there is no need for second law. It is the second law of thermodynamics which define a new state function called entropy. Thus, function entropy along with the other function like free energy G is used to predicate whether a given process is spontaneous or non-spontaneous. As stated by the first law, the exact equivalence between heat and water is not possible. First law established the relation between heat absorbed and work done by the system. According to first law, when heat is converted into work, the work is done is equivalent to the heat absorbed. While it is seen from experience that work can be complete transfer into heat, but heat absorbed cannot be completely converted into work without leaving some change in system or surrounding. Thus, this observation cannot be explained by the first law. The second law, which helps us to calculate the maximum fragrance of it that can be converted into work from a given process. Thus, the first law of thermodynamics is not sufficient, and therefore an additional law which explains the above limitation is necessary. Before taking up various statements of second law of thermodynamics, we discuss what is a cyclic process and the Carnot cycle. Then various statements of second law of thermodynamics can be easily understood. Cyclic process. In a cyclic process, a system after undergoing a series of changes return to its original state, as shown in Fig. A cyclic process. A system undergoes change from state A to state B by path 1 and return to original state by path 2. This is a cyclic process. The net change of internal energy in a cyclic process is 0. Delta U is equal to 0. Therefore, according to first law, delta U is equal to Q plus W. 0 is equal to Q plus W. Q is equal to minus W for a cyclic process, or when the cyclic process is carried out at constant temperature, the cyclic is said to be an isothermal cycle. If the process is carried out in infinitely small step, the cycle is said to be a reversible cycle. Although reversible process is only imaginary and cannot be brought into a practice, but concept is quite useful is driving some important relationship. The most well-known cyclic process is a Carnot cycle. The Carnot cycle the Carnot cycle was named after a French engineer, Sadi Carnot. He was interested in the efficiency of steam engine and other heat engine, the device which convert heat into work. He observed that maximum conversion of heat into work is possible in a cyclic process in which all the necessary steps are carried out reversible. Such a reversible cycle is called a Carnot cycle, and a engine operating on the basis of this hypothetical cycle is called Carnot engine. An expression for the efficiency of a Carnot engine may be derived using a Saint-Schmidt diagram as shown in figure number 2. Now we can see that 4 different operation of Carnot cycle. The system consists of a 1 mole of an ideal gas filled in a cylinder which is insulated and fitted with frictionless piston. The gas is brought in a contact with two heat reversible source at T2 and sink at T1, which are maintained at constant temperature, whereas T2 is greater than the T1. The Carnot cycle involves 4 reversible steps as shown in figure number 2. Isothermal expression, adiabatic expression, isothermal compression, adiabatic compression. The processes are represented on a pressure volume diagram in figure number 3. Step 1. Isothermal reversible expression. The cylinder containing 1 mole of ideal gas having volume 1 is placed on the source of heat reserve at temperature T2. The gas absorbs quantity of heat Q2 and undergoes isothermal reversible expression to volume V2 indicated by the curve AB. The work done by W1 by the system is given by minus W1 is equal to RT2 in V2 by V1 equation number first. As in isothermal process, delta U is equal to 0. The work done is equal to the heat absorbed Q2. Sum that minus W1 is equal to Q2 is equal to RT2 in V2 by V1. Equation number second. Work done by the system is taking as negative according to the IUPAC convention. Step 2. Adiabatic expression. The cylinder is removed from the source and kept on the insulating base. The gas is allowed to expand adiabatically from volume V2 to V3. In this step, by temperature decreased to T1, the temperature of the sink. This path is shown by the curve BC in figure number 3. The heat absorbed by the system is 0 as expression takes place under adiabatic condition. The work done by the system is W2 is given by minus W2 is equal to CV bracket T1 minus say T2 bracket. is equal to minus Cv T2 minus K T1. Equation number 3, where Cv is heat capacity of ideal gas, work done is negative by usually convention. Step 3, isothermal compression. The path is shown along the curve CD in fig number 3. In this step, the cylinder is removed from the insulating base, is kept in contact with the sink at temperature T1. The gas is compressed isothermally till the volume decreases from V3 to V4. The work done on the system is positive by convention and is given by W3 is equal to RT1 in V4 by V3. An amount of heat WQ1 bracket having negative sign exactly equal to W3 will be returned to the sink. Thus we can write minus Q1 is equal to W3 in RT1 in V4 by V3. Equation number 4, adiabatic compression. In this step, the cylinder is removed from the sink and placed on insulating base. The gas is compressed adiabatically along the curve dA. The volume reduced from the V4 to V1 and the temperature of the gas rises from T1 to T2. The work done is positive by convention and is given by V4 is equal to Cv bracket T2 minus K T1. Equation number 5. As a result for operation, the system returned to its original state and reversible cycle is complete. The work done W in this cycle given by work is equal to minus K work done 1 plus minus K work done 2 bracket plus work done 3 plus work done 4. RT2 in V2 by V1 minus Cv bracket T2 minus KT1 plus RT1 in V2 by V3 plus Cv bracket T2 minus KT1. RT2 in V2 by V1 plus RT1 in V4 by V3. Equation number 6. Net heat absorbed Q is given by Q is equal to Q2 plus bracket minus 1 bracket RT2 in V2 by V1 plus RT2 1 in V4 by V3. Since point T2 V2 and T1 or V3 lie on same adiabatic curve BC and T2 V1 and T1 V4 lie on another adiabatic curve AD. Then we're using expression TV raised to power gamma minus K1 and constant. We can write T2 V2 raised to power gamma minus K1 is equal to T1 V3 gamma raised to power minus K1 and T2 V1 gamma raised to power minus K1 and T1 V4 gamma raised to power minus K1. Equation number 8. Dividing equation number 8 and 7, we get V4 by V3 is equal to V1 by V2. Equation number 9. Substitution for V4 by V3 in equation number 6, we get W is equal to RT2 in V2 by V1, RT1 in V1 by V2, RT2 in V2 by V1 minus RT2 1 in V2 by V1. Equation number 10. W is equal to RT bracket T2 minus KT1 in V2 by V1. Equation number 11. For the above derivation, it is observed that the work done in a Carnot cycle is only the work involved in the isothermal operation, because the work done in a adiabatic operation cancel one another. Efficiency of Carnot cycle and Carnot theorem. The efficiency of denoted by N of the Carnot cycle or heat engine is defined as the ratio of work done by the system to the amount of the heat absorbed at high temperature. Thus N is equal to W by Q2. Equation number 12. Substituting the value of W and Q2 from equation number 11 and 2 respectively, N is equal to R bracket T2 minus KT1 in V2 by V1 by RT2 in V2 by V1 is equal to T2 minus KT1 by T2. Equation number 3. For Equation third, it is clear that the efficiency of reversible heat engine depend upon only the temperature of source and the sink and is independent of the nature of working substance. In other words, all reversible heat engine working between the system two temperature have the same efficiency. Also, the efficiency of the reversible heat engine is maximum for given temperature. This is called a Carnot theorem. Thus, the efficiency of heat engine operating in a Carnot cycle depend only on two temperature at which engine operate. The greater the difference between T2 and T1, greater is the efficiency. For a cyclic process, net heat absorbed is equal to net work done. Q2 minus Q1 is equal to W. Therefore, N is equal to Q2 minus Q1 by Q2. Equation number 14. For equation 13 and 4th, N is equal to T2 minus T1 by T2 is equal to Q2 by Q2 minus Q1 by Q2. Equation number 15. Two important conclusions arise from the equation number 15. If T1 is equal to T2, then no work is done in Carnot cycle. This is more clear for equation number 10. When T1 is equal to T2, then the work is done is isotherm expression at temperature T2 will cancel out the work done by the system is in isothermally expression at the temperature T1. In other words, in a Carnot cycle, no heat will be converted into work if only isothermal expression and compression above are carried out. It's follow from equation number 15 the efficiency of N of Carnot cycle will be unity if T1 is equal to 0 as T1 can never be 0, therefore T2 minus T1 by T2 is always less than the unity. Hence, the efficiency of heat engine is always less than unity. Thus, only a fraction of heat absorbed at a high temperature can be converted into work. Statement of the second law of thermodynamics. Having discussed the cyclic process of heat engine, we can move now given the statement of second law, which can be easily understood from the efficiency of Carnot cycle. Kelvin statement: since T2 minus T1 by T2 is less than the 1, it is follow that W is less than Q2, work is done is less than the heat absorbed. Thus, this means that only a part of heat absorbed by a system at a high temperature T2 is converted into work. The rest of heat Q1 is given out by the system to surrounding, where it is the lower pressure temperature T1. Based on the observation of Kelvin state the second law of thermodynamics as follows. It is impossible to use a cyclic process to transfer heat from a reserve and convert it into work without at the same time transferring it from hotter to colder body. It can also be stated as it is impossible to convert heat completely into work without leaving some effect in the system or surrounding. Although the second law has been stated in number of ways, but all these statements have some fundamental concept. Work can also be converted into heat, but the conversion of heat into work does not take place under all conditions. Kelvin Planck statement. We have seen that the work done by a heat engine operating in a cycle is zero when the two temperatures are same. The Kelvin Planck statement of second lies. It is impossible for a system operating in a cycle and connected to a single heat reserve to produce a positive amount of work in the surrounding. In other words, it is impossible to contract a perpetually machine which operates solely by removal of the heat from a thermal reversible. Celsius statement: a heat engine operating in a cycle can perform work only by absorbing heat from a reserve at high temperature by rejecting the difference between heat absorbed and the work done by engine to another reserve at low temperature. On this fact, Celsius statement of second law is based off Celsius statement of second law of thermodynamics. It is impossible to contract a machine that is able to transfer heat by cyclic process from colder to hotter body without use of any external agent.